So when I introduced sound, I said that when made to vibrate, mass produce sound, and that all objects have natural modes at which they like to vibrate. And I called these modes resonant frequencies. And then I also linked in and said that these resonant frequencies are creating standing waves. So every time that we create sound, or if I have a tuning fork here, something is vibrating in a standing wave pattern. And so what we're going to do is look at, expand what we've done with standing waves already to systems like tubes. And I'm going to do a bunch of demonstrations in this video so we can talk about it. And then in the next video, we're actually going to go to the whiteboard paper and we're going to do the math about it so we can see it. So I have here an exercise band. Let me just show you what I can do with that. If I just set that up, right, and listen. You can hear that sound. I can change that sound by changing the tension of the band, or just simply by changing the length of the band. But you'll notice the way that it vibrates, it's vibrating in a standing wave pattern. The top and the bottom, you can't see the bottom, are not moving, they're nodes, and I have my antinode point here. It's actually at the n equals 1 standing wave. So most strings or elastic objects, when they're made to vibrate, like say a rubber band here, this is vibrating in a standing wave pattern specifically at the first harmonic. Now here, why is that sound so much higher pitched than the other sound? And if you remember from what we talked about, the smaller the length, the higher the frequency. But there are more factors involved, and that's kind of what we want to talk about. So I'm going to show a couple demonstrations with this as well. And what we're going to see in the math about this is what those other factors are. But remember, shorter length, higher frequency. That's important. There are other factors, as I said. So here we go. If I have a straw, right, and I blow over the top of it, we've all done this, right? Right? Creating essentially a slide whistle, right? But that's a little bit different as well than the string, because here what's vibrating is not the straw, but the air column inside the straw. And so what we're doing is we're creating a standing pressure wave, which we can draw as a transverse wave in terms of what that pressure looks like, so we can more easily visualize it as if it is a string. But it's a little bit different. Let's just show why. I have 2 cardboard tubes here. Which do you think, when I blow across the top of it, is going to create the higher pitched sound? Well, let's listen. Right? Hopefully you hear that this is the higher pitched sound. Shorter length, higher pitch, right? But there's something else that I can do. Let's look at the cardboard tube, right? It's almost like I'm playing a flute, because that's essentially what a flute is. It's just a tube. And then what we're doing by, if you are, opening and closing the keys, all you're doing is you're changing the length of the tube, or the effective length of the tube. And we're going to see why the length of the tube matters in a little bit. But there's something else that matters, because listen. Notice when I close one of the ends off, it changes the pitch. So an important factor when we're talking about tubes is not only going to be just the length of the tube, but something that we're going to call the boundary conditions. Whether the ends of the tube are open like this or closed like this, right? So this would be a tube with both ends open, and this would be a tube with one end open, one end closed, which is called the closed tube. I know that's weird because both ends aren't closed, but generally we don't make an instrument with two ends closed because how are we going to vibrate the air inside, right? So closed tube, one end open, one end closed, open tube, both ends open. And we're going to look at the math of that. I do want to show you just one other, I don't know if you've ever seen this, right? But if I just twirl this, actually I'm not sure if you're going to be able to see it. I have to, it produces a constant tone, a constant pitch based on the length of this tube, both ends open. So if I then listen to this, I'm going to spin it faster and faster, right? And so you notice it produces very that ooh, ooh, ooh tones. And we're going to find out that those are in a particular mathematical progression. With this particular instrument here, to lack of a better phrase, I can force it to vibrate at several of its harmonics based on how fast I rotate it. So here's the fundamental for this tube. And then next harmonic. And I barely got up to the one after that, but hopefully you could hear that. And so that's what we're talking about here, is the math of standing waves with columns of air. And we're going to look at the difference between open and closed tubes. But first, we're going to start by reminding ourselves the logic of what we said about standing waves and strings, and then extrapolate that out to tubes.